Hello students, in this video we'll see how to solve an ordinary differential equation around an ordinary point. Let's recall the second order differential equation. If I have a of x y double prime plus b of x y prime plus c of x y equals 0 has an ordinary point at x equals x0 if a of x0 is not equal to 0, okay? At an ordinary point, I know that there's a convergent power series solution to this differential equation. So the ODE has a convergent power series solution centered at x0. We'll prove that in a further video, okay? So let's do an example of this and see how it works in practice. So here's our example. If I wanted to solve y double prime plus, let's say, 3x y prime plus 3y is equal to 0, I've given a very simple example where the a of x here is just equal to 1. So a of x is 1, which means that there every point is an ordinary point for this differential equation. So here every point is an ordinary point. Okay, so I'm going to just focus on the ordinary point 0 and then look at find a Maclaurin expansion, right? So let's consider the Maclaurin expansion of a solution y. So y is going to be the sum, n goes from 0 to infinity, of some numbers a n x to the n, okay? And so now the scheme by which we solve these differential equations is fairly simple, so let's do it. And so what's the idea? The idea now is that if that's the case, then what can I say about y prime? Then y prime is going to be the sum, n goes from 0. I'm going to leave the 0 in there for simplicity, of n, a, n, x to the n minus 1. And of course, you might say, why didn't you start the sum at 0? Because the sum really starts at 1. I'm going to leave it at 0 because we're going to start shifting indices later on. So leaving everything at 0 to start is the easiest way to solve these problems. And then y double prime is going to be what? It's going to be the sum, n goes from 0 to infinity, of n, n minus 1, a, n, x to the n minus 2, right? Okay. Of course, when n is equal to 0 in this first sum, I get nothing. When n is equal to 0 or 1 in this second sum, I get nothing, right? So in other words, these sums really start, this first sum starts at 1, that sum starts really at 2, right? So now we're going to plug these series into the differential equation, and what are we going to get? So the first term over here is going to be the sum, n goes from 0 to infinity, of n, n minus 1, a n, x to the n. Okay, that's what y double prime is. So this term over here goes right over here. Then I have a 3x y prime. Well, if I multiply the y prime by x, what's going to happen to that negative 1? If I multiply the 3x by that x to the negative 1, it's going to turn into x to the n, right? So the next sum is going to be the sum. That's why we've sort of kept it at 0. N goes from 0 to infinity, of 3 times n times a n x to the n, right? So in other words, I have a 3 times n times a n, and then x to the n. And then this last, so this term over, this sum over here really goes right over there, like that. And finally, I have 3. Sum n goes from 0 to infinity, of 3 a n x to the n has to be equal to 0. Okay, excellent. So I'm going to group those those last two series together, and then what will we have? So if I do that, we're going to have this first series over here, the sum, and now I'm going to write it as 2 to infinity, n minus 1, because the sum really doesn't have a 0, doesn't have a 1. So now I'm going to shift everything to 2, a n x to the n. Nothing changes there, because when I plug in 0 or 1, those first two terms are gone. So the sum really, in fact, starts at 2, right? And then what we'll have, then we're going to have the sum, n goes from 0 to infinity. Then I'll have a 3n, and then a plus 3, a n x to the n is equal to 0. Now these sums are out of sync with each other, right? So here's what we're going to do. We're going to take this n over here and turn this n right over here into a 2. So n's going to go from 2. So I'm going to add 2 to the indexing set here, which means over here we're going to have to subtract 2 from every n. So this is going to be a 3 times n minus 2, and this is going to be an a n minus 2, and that's going to be an x to the n minus 2, okay? And now both sums start at 2, so I can add them together. And I know that an infinite series vanishes if and only if the coefficients vanish. So what this is going to tell me is this is going to tell me that I can conclude from this that n over here, that the coefficients have to vanish, right? So I have n times n minus 1, and then plus, that's an an, plus 3 times n minus 2, an minus 2, has to be what? Has to be equal to, and of course this is an n minus 2 over here, so my second derivative is an n minus 2. So that's an n minus 2, that's an n minus 2. There we go. That makes more sense. Good. And excellent. And so now we have what? This has to be equal to 0 for n bigger than or equal to 2. And of course, a0 and a1 are arbitrary in this problem, right? So let's see what this will tell us over here. This is going to tell me that an is equal to what? An is equal to negative 3 n minus 2 over n times n minus 1 an minus 2. Okay? Now, what will happen is that this is going to give me a relationship between the even a's and the odd a's, right? So in other words, once I specify a0, it'll specify the rest of those of the even a's. So let's see what happens then. So let's do some examples of this. So of course, what does that tell me? It first tells me that a2 is equal to what? Is equal to negative 3. So I'm going to plug in n equals 2, right? And then I will get what? So if we plug in n equals 2, and so we forgot the plus 3 over here. So that's a plus 3. So let's change that a little bit. So what will happen over here? So let's change this a little bit. So we forgot the plus 3 because that gave us a nonsense. So let's fix that over there. So this is really going to be what? This is going to be an 3n minus 2 then plus 3, right? So that's going to be a 3n. So let's change that to a what? That's going to be a, so let's change our notes a little bit. Apologize for that. We're going to have a what? We'll have a 3n minus 6 plus 3. That's a 3n. And then a minus 3, an minus 1, 2 is equal to 0 for n bigger than or equal to 2. Excellent. And so now, of course, what will happen? So now the n minus 1 is going to cancel. That's an n minus 1 over here, and this is an n minus 1 times 3, so that's going to turn into a 3, right? And so our conclusion now is that an is equal to negative 3 an minus 2, that's much nicer, over n, like that. Excellent. So now let's run this argument for the evens. So for the evens, that says that a2 is going to be negative a3 a0 over what? I plug in n equals 2. a4 is going to be negative 3 a2 over 2, et cetera, et cetera, et cetera. That says that a2n is equal to negative 3 a2n minus 2n over 2. And now here's the cool part of this argument. The cool part is that if I take all these expressions over here and multiply them, I'll have what? I'll have a2 through a2n, I'll have a0 through a2n, so all the only a's that are going to survive over here after cancellation are the a0 and the a2n. So I'm going to conclude that a2n is equal to what? Is equal to negative 1 to the n. There's negative 1 negative signs when I multiply those things. And a0, and then a 3 to the n, and a0, and then a 2 to the end of the denominator. So I found a representation for all the even coefficients. So this is going to give me a solution over here. One of my solutions, my y1, is going to be what? Is going to be a0, and then the sum, n goes from 0 to infinity, of negative 1 to the n, 3 to the n, over 2 to the n, and those are the even coefficients. So that's going to mean x to the 2n. So I get one solution from the even coefficients, which is this function over here. Now let's turn to the odd coefficients and see what happens. So if I turn to the odd coefficients, I'm going to have what? I'm going to have a3 is equal to what? a3 is equal to negative 3 a1 over what? I have to plug in n equals what now? I have to plug in n equals 3. So I'm going to have a 3 over there. Let's leave it like that. a5 is going to be what? Negative 3 a3. And I have to plug in n equals what? I have to plug in n equals 5 now, right? So I have 3 times, I have 5 down over there. And then generically, a 2n plus 1 is going to be negative 3, a 2n minus 1 over a 2n plus 1. And so by this reasoning over here, I can write down the solution for the odds. So what will the odd solution be? So the odd solution is going to be y2. It's going to be an a1, the sum, n goes from 0 to infinity. And then what? And then we're going to have a negative 1 to the n. We'll have a 3 to the n. We'll have an x to the 2n plus 1. Those are the odds. And then where do we start over here? We're going to start, we'll have a 3 times 5 times 5, all the way down to product up to 2n plus 1 like that, okay? And so now we have the second solution over here. And so now any solution of our differential equation over here, so in other words, this is an even function, this is an odd function, so our general solution over here to our differential equation is going to be y is equal to c1 y1 plus c2 y2, and those solutions are independent and they both solve the differential equation, so I have a general solution of this second order homogeneous linear differential equation by the method of Frobenius, or the method of around an ordinary point. Thank you very much.